welcome back once again to Ask IITians. Now continuing with the previous lecture where we have done something about what do we mean by ideal gas, what were the different laws corresponding to the ideal gas. Now it's a time when we should begin over to find out what is the pressure exerted by the ideal gas on the walls of the container. So I'll try to tell you a derivation for how the gaseous molecules are assumed to move towards the walls of the container, and then corresponding to all this derivation will finally prove out the pressure which is exerted by the molecules of the ideal gas on the walls of container. Once we are done with this thing, I'll also try to correlate everything related to this with the kinetic theory of gases. So let us begin up with the session so that you can understand both these 2 points. So students, now let's once again begin with the kinetic theory of gases. Now let us study some of the postulates which are basically related to the kinetic theory of gases. So what are the postulates? Let me speak them out one by one. The first postulate says that the macroscopic behavior of any ideal gas can be described by using the equation of state. But if I am talking about the microscopic behavior, that can only be described by the kinetic theory of gases. That means what? Whatever we have learned so far is good enough in order to describe the macroscopic behavior of the ideal gas. Whereas, if I want you to go into the deeper details about the microscopic behavior, then you need to go by the kinetic theory of gases. Now, the assumptions which are to be taken in order to understand the kinetic theory of gases are: it supposes that all the molecules are made up of identical atoms or molecules. That means if I am taking a particular gas, that particular gas is made up of all the identical atoms and molecules. Now, all the atoms or the molecules may be moving randomly and haphazardly. So that means there is not a fixed movement. Each and every single atom will be moving in a random fashion. Moreover, it says that the volume of the atoms of the molecules is very negligible when it is compared to the volume occupied by the gas. For example, if you are taking a container and let me say the volume of the container is V, and there is some gas which is filled inside the container V. Now, if you collectively find out what is the volume of all the atoms or all the molecules, then the total volume which is occupied by all the atoms or the molecules is found to be very small as compared to the total volume of the container. Moreover, it has also been said that the intermolecular forces are negligible except during collisions. That means when one molecule is colliding with another molecule, whatever is the intermolecular force between the two atoms, that will be negligible. That means no two atoms are gonna combine with each other or they're gonna repel each other because the intermolecular forces of attraction are negligible. Then it also says that the interatomic or the molecular collisions are elastic. Now what do we mean by elasticity of the collision? Whenever one atom is going to collide with another atom, that means there will be no loss of any energy. So the collision will be perfectly elastic collision. There won't be change in the shape of the molecule. There won't be change in the energy of the molecule. If I continue with the assumptions, I'll say that the duration of a collision is negligible compared with the time spent traveling between the collisions. For example, if I simply say you that there is an atom over here and another atom is here, and if the two atoms 1 and 2 are going to collide with each other, the time that they'll spend during the collision is again negligible as compared to the time they'll spend in order to come close to each other. Moreover, another assumption says that atoms and molecules move with constant speed between the collisions. Gravity has got no effect on the molecular motion. So for example, if you say that there is some air inside this room, then I will say that the gravity has got no influence over the molecules. That means molecules have got no tendency to settle at the bottom of the room. Moreover, these atoms and molecules are moving with a constant speed between the collisions. For example, if one is getting collided with the second atom, the velocity with which it was moving and the velocity with which this is moving will be constant between the successive collisions. Now, once we are done with the assumptions for the kinetic theory of gases, let us now move forward as to calculate what is the force which is exerted by the ideal gas. So in order to find out the force which is exerted by the ideal gas, let me consider an ideal gas which contains n molecules and it is contained in a cubical container of side D as shown in the figure. So see, there is a figure which has been shown. You consider it to be a cube and the side of the cube is D. That means all the sides are of length D. And we can say that there are total number of n molecules of the gas which are present inside the container. Let each molecule of the gas is having the mass m and the velocity v. So each and every small molecule of this gas inside the container has got the mass m and the velocity v. Now the velocity of each molecule can be resolved into the three components. I'll say Vx, Vy and Vz. Let me say, for example, you consider an atom here of mass m. Since the overall velocity is given as v, so we can genuinely find out the components of velocity in all the three x's, right? So we can have a Vx component, we can have another Vz component, we can have Vy component also. That means this V is gonna be the overall velocity of the molecule in all the three directions. Now continuing with the same fact again, let us say consider initially a single molecule was moving with the velocity Vx towards the wall A. Let me say the same cube which I had taken earlier, this has got the wall, let me call it as wall A and let me call this as wall B. So I am saying, let us say this molecule is moving with the initial velocity Vx in the direction of wall A. Then and after colliding elastically, I am saying that when the molecule was moving with the velocity Vx towards a wall A, it got elastically collided, and once it was coming back, it is coming back with the same velocity but in the opposite direction with the velocity as minus Vx. This is before the collision and this diagram is after the collision. Now once we are done with this thing, can I say that the change in the linear momentum of the molecule? We know that the momentum of the molecule is given as P is equal to mass into V, velocity. So when it was moving towards the wall A, the momentum was, let's say, minus Vx. Now once it is moving in the direction opposite to the wall A, the momentum will be having a different direction. So the change in momentum will be nothing but minus mvx minus plus of mvx. So earlier these were having opposite direction and I just subtracted the two, and hence delta px is written as minus 2 mvx. So I'll simply say that the molecule has to travel a distance 2d from A to B and back to A before its next collision with the wall A can be effected. For example, this was the wall and this is another wall. Let's say this is A, this is B. That means the molecule has to go to the distance D, get collided with the wall B, and then again come back to the wall A, and then only it will get collided. That means before the second collision can take place, the molecule is going to travel a distance of 2d. This is what has been written over here. So we know what is the change in the momentum. Also we know what will be the time taken because the velocity is known to me. So the time taken will be the total distance traveled 2d divided by the velocity in one direction, that is Vx. So now you know what is the change in the momentum and what is the time with that momentum is changing. If I continue with the further thing, I can say that if Fx1 is a magnitude of the average force exerted by the molecules on the wall in the time delta t. So you have that time period delta t as that time span. And let me say that Fx1 is that particular magnitude of the average force which is exerted by the molecules in time delta t. So if you apply the Newton's second law of motion, you can very easily say that the force exerted is nothing but the change in momentum with respect to the change in time. Or if I say that the force can be defined as the change in momentum with respect to the time in which that change took place. So I will simply say that Fx1 is nothing but delta px divided by delta t. You know the value of delta px 2mvx and you know the value of delta t 2d by vx. So if you correlate the two things, you will get the value of force as m divided by d into vx square. Now we know that there is not a single molecule which is there inside the container. There are n molecules of the ideal gas inside the container. So the total force Fx will be written as m So the total force will be written as Fx as m divided by d into Vx1 square plus again m divided by d into Vx2 square, and hence up to total number of n molecules. So if I ask you to take m and d outside, so you will say Fx is nothing but m by d Vx1 square plus Vx2 square plus Vx3 square up to Vxn square. Now since we have reached till this point, if I continue ahead, where I simply say that Vx1 is the x component of the velocity of the molecule 1. That means if I am just taking into account the molecule 1, and if I suppose that the molecule 1, since I told you it is moving in all the three directions, so Vx1 is just the component of the velocity with which 1 is moving in the x direction. So Vx2 is the x component of velocity of the molecule 2, and so on. So the mean average value of the square of velocity. So I'm talking here about the mean average value of square of velocity in the x direction for all the n molecules thus can be stated as, see, you have Vx1 square, Vx2 square, Vx3 square, Vxn square. That is nothing but the square of the velocity of n molecules in x direction. You divide by the total number of molecules, you will get the mean average square of velocity in x direction. Now, if I write this thing, you can also take n to the left hand side and it becomes n times Vx square average is nothing but this particular value. So, having done till this, now let me move ahead. So, I'll say the x component for the total force exerted on the wall of the cubical container is nothing but, now see, you know what is the velocity, so you can find out what is the total force with respect to x direction which is exerted on the wall of the cubical container. So Fx is m by d into capital N Vx square. That means nothing but I have just substituted the values. Now, we know, right, the magnitude of the velocity v, since the velocity v is actually there in all the three directions. So, the magnitude of velocity we calculate as under root Vx square plus Vy square plus Vz square. If I ask you to take the square on both the ends, you will get V square is Vx square plus Vy square plus Vz square. So I can very easily correlate that if I am taking the average of the square velocity, it will be equal to average of Vx square plus average of Vy square plus average of Vz square, which has been shown in the above equation. Now, since the velocity of the molecules in the ideal gas are completely random, this was the one of the postulates I told you in the beginning of the lecture, that all the molecules are randomly moving. Randomly moving means some will be moving in x direction, some in y and some in z direction. So I can say there is no preference to any one or the other direction. X is also same for me, y is also same for me, as well as z is also of equal importance for me. Hence, I will say that the average velocity in Vx direction will be same as the square in y direction will be same as the square in z direction. So, I can very simply equate, since v square was nothing but Vx square plus Vy square plus Vz square, and since these three are equal in numbers, so I can say this comes out to be 3Vx square. That means if I am asked to find the value of average velocity square only in x direction, I can correlate it to this value. So the total force exerted on the wall in all the directions, since earlier I just found out what was the total force in x direction. Now I need to find out what is the total force in all the directions. So that total force in all the directions will be F is equal to m by d into n. Then it is to be multiplied by average of Vx square. That means m by d into n. This Vx square we just got the value as v square over 3. That means if you take n outside and if you do the correlation between the stuff, f will be written as n over 3. You take m and d inside the bracket. Now where v square is nothing but the mean square velocity of the molecule. So let's read it from back. There is a molecule, you know the velocity of the molecule is v. You take the square of the molecule as v square. Then you take the mean or the average, which is v square. So if you are done till this point and if it is completely clear to everyone, let's move again with the pressure of an ideal gas. So from the definition of pressure, we know that pressure can be simply written as force per unit area. Now area of the wall is nothing but d square. Why? Because d is the length of or the edge of the cube. So force can be written as n over 3 into mv square over d, the one which we got in the previous slide. Now if I just substitute the value of F in the equation of pressure, I will say 1 by 3 n mv square over d cube. So a square area is d square, you multiply this d with another d in order to get a d cube. Now we know for any cube the volume is given as length cube. So we can say P is equal to 1 by 3 m into n by v into v square. Now, if I try to correlate this thing and if I try to give you a little more information about this equation, we can say that P times V is 1 by 3 n into m into V square. And hence, we can simply say that where this n into m is known as the mass of the ideal gas inside the container. Because n is the number of moles, total number of molecules, and m is the mass of the molecule. So n into m is the total mass of the gas inside the container. And hence I can also write it as P is equal to 1 by 3 rho times V square. Now how to define this rho? I will simply say that since the density of gas is rho, it is given as, I told you, so we just know that density is nothing but mass per unit volume. So just now I told you the total mass is n multiplied by m and the volume is V, which is nothing but rho. So I just substituted over the value and hence the equation is written as this, where P is nothing but the pressure by the gas, rho is the density of gas, V square is the mean square velocity of the gaseous molecules. Now, let us define something as what do we mean by root mean square velocity. So, let me now again read it from the back. Velocity was V. If I am taking the square, it becomes V square. If I am taking the root mean, it becomes V square. And if I ask you to take the root, you get this value. So, if you are asked to go in the backward direction, you can very easily define root mean square velocity as V square. So, just go step by step in the backward direction. Since we have just learned that PV is equal to nRT or PV is equal to nkBT from the equation of state, if I am writing it in terms of Boltzmann constant, so can I very easily correlate? I know PV is nothing but 1 by 3 into n into m into V square. Also I know PV is equal to nkBT. Correlating the two things, you will get nkBT is 1 by 3 n into m in V square. And hence, if I ask you to calculate the value of V square, so you can say V square is nothing over 3 kBT divided by n. So, once we got up to this point, we can very easily say that Vrms is nothing but the square root of the earlier value. So, it will be root 3 kBT over n. Or this Vrms can also be written as under root 3 RT by capital M. So, we must keep in mind what do we mean by these four symbols. Vrms is nothing but the root mean square velocity and this is nothing but the speed. So, m is the mass of molecule gas, whereas capital M is the molar mass of gas. Molar mass means the mass of 1 mole of gas and T is the absolute temperature. Hence, just going back to the previous equation, we can correlate since P is equal to 1 by 3 rho times V square, so V square average can be written as 3 times of P divided by rho. Therefore, the equation of root mean square velocity of the gaseous molecules can again be written in the terms of pressure and density with respect to this formula. Now, since we have done a lot much about the kinetic theory of gases, how you are going to represent the pressure and the volume in the terms of ideal gas equation as well as in the terms of kinetic theory of gases, let's try to correlate it with a few examples. So, let me read the question. So, it says that 8 gas molecules which are chosen as random are found to have the speeds of 1, 1, 2, 2, 2, 3, 4 and 5 meter per second. And we have been asked to determine the mean speed of molecules. the mean square speed of molecules and the root mean square speed of molecules. Now if I am asked to do this question, let's go one by one. So first let us find out the mean speed of molecules. If I am asked to find out the mean speed of molecules, that is nothing but a very simple question where V will be written as sigma Vi, I is equal to 1 to n divided by n. Hence, V can be written in this case as 1 plus 1 plus 2 plus 2 plus 2 plus 3 plus 4 plus 5 divided by 8. If I ask you to calculate it, it comes out to be nearly 2.5 meters per second. So, let me go over to the second point where I have been asked to calculate, since now I know n is equal to 8. I have been asked to calculate mean square speed of the molecules. So, how to calculate the mean square speed? You can simply say that V square average is nothing but sigma I is equal to 1 to n, Vi square divided by n again. So, if I ask you to write the values, you will get 1 square plus 1 square, 2 square, 2 square, 2 square, 3 square, 4 square, 5 square divided by 8, and the value comes out to be nearly, so this value will be whatever you will be calculating, so the value comes out to be in this particular thing. But what is important in this case will be meter per second is the unit, then square, and then the total number. So you have meter square per second square. Now this value comes out to be, I think, nearly 8 meters square per second square if you're just gonna calculate it. So if I come over to the third part, which says that you need to find root mean square velocity or root mean square speed. So we know V RMS is nothing but under root of V square average, that means under root of 8 meter square per second square, which comes out to be 2.83 meter per second. So please do take care of the units while you are doing such questions. These questions are not difficult, but what is important is to keep in mind how the units are to be used up. Let's try to do one another example on this basis. It says that a cylinder of volume 0.08 meter cubes contains oxygen at a temperature of 280 Kelvin and a pressure of 90 kilopascals. You have been asked to determine the mass of oxygen in the cylinder, the number of oxygen molecules in the cylinder, the root mean square speed of oxygen molecules in the cylinder. And the data point that you have to keep in mind are R is given to be 8.314 joules per Kelvin per mole, K is given to be 1.38 into 10 raised to the power minus 23 joules per Kelvin, molar mass of oxygen is 32 grams per mole, and Na is 6.022 into 10 raised to the power 23 mole inverse. Let's see how we are going to do this question. Simply if I ask you to first of all use the values, you will say since volume is given to be 0.08 meters cube, temperature is given to be 280 Kelvin, pressure is given to be 90 kilopascals. 90 kilopascals is nothing, 90 into 1000 Pascal. So if I ask you to correlate the value, you can very easily write 90 into 10 raised to the power 3 into 0.08 is nothing but given mass divided by molar mass. Now since everything is in the SI unit, so please convert the molar mass also in the SI unit into 8.314 into 280. So do take care of the units which you have mentioned. So the mass which you will be calculating from this particular equation will come out to be 9.90 into 10 raised to the power minus 2 kgs. And hence this is the solution for the first part. Now let us move over to the second part where I have been asked to calculate the number of molecules of oxygen in the given cylinder. Now I know that given mass divided by molar mass is nothing but the number of moles which are present. So I can very easily correlate that N is nothing but given mass by capital M into Na. If I ask you to put up the values, given mass is 9.90 into 10 raised to the power minus 2 divided by 0.032 into 6.022 into 10 raised to the power 23. So the number of molecules actually come out to be approximately 1.86 into 10 raised to the power 24 molecules. So having done with this B part also, let us come over to the C part where we have been asked to find out what is the root mean square velocity. Now we know very easily RMS is nothing but under root 3 RT by capital M. The molar mass So it is 3 into 8.314. The temperature was 280 divided by 0.032. And if I ask you to calculate, the value will come out to be nearly 467 meters per second. So students, this was all about how we are going to use the kinetic theory of gases, and we are going to do the numericals and the examples on this basis. Students, here at Ask IITians, we provide you a very good opportunity where you can ask your doubts also if you have any doubt regarding any topic. For that, you first of all have to go on to www.askiitians.com website. If you open the page, you will find a topic as Ask a Question. So you can click at that link, Ask a Question. At the right hand side, you will get something where you will have to first of all select a category. The different categories that will be available, like it will be, you can have physics, you can have a question from maths or chemistry. So suppose I select a question from chemistry, then here you can also attach the image of the question if you have in account. Else you can type your question here and finally click over to get an answer. As soon as you type something over to get an answer, you can ask the question from your respective teacher. So hope this also helps you out and your query will be solved. So students, you saw how we discussed something about what do we mean by ideal gas equation, and finally how did we derive the formula for the pressure exerted by the ideal gas on the walls of the container. You have also seen that we have discussed something about the kinetic theory of gases. The assumptions and everything related to the theory of gases was discussed. Now we have also done certain examples related to the same. So I'll ask you once again to join me up in the next session so that we can discuss a little more about the different derivations which are to be dealt in this chapter. So by that time, study well, stay tuned and be there in the next session.